Hello, I'm Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm a robot doctor. Today, I want to show you one of my flying robots. Well, that didn't work very well. What went wrong with the robot? Why did it crash? The goal of this series is to explore how robots solve the problems that allow them to be useful in the real world. And we can do it with the math you may already know: geometry, trigonometry, algebra, and some concepts from physics. We'll even help you brush up as we go along, but be prepared to take notes. In Lesson 102, I'll tell you about something called the Sense, Plan, Act framework. This is a framework typically used by modern robots. It organizes how they see the world, how they think, and how they act. We will also talk about some of the broad requirements for getting a robot to perform work. But first, some basics. What is a robot? What does it do?
What's the definition of a robot? Most of us know one when we see one, but what makes it different from other machines? We can start with this sentence: a robot is a computerized machine. That definition can be quite broad, and most people would not consider their car or their microwave to be a robot, yet both of those are machines with computers. How about a robot is a computerized machine that looks like a person? Better, but not all robots look like the robots you see in movies. Real robots don't always look like people, but they can still do some tasks like people can.
So how about this one? A robot is a machine that can move independently and perform complex actions similar to a living creature. That's the definition from the dictionary, and it's a pretty good one. It has two key elements. First, the ability to move independently, and second, the ability to perform complex actions. The ability to move independently requires that the robot can act. When the robot's software tells it to move in a particular way, the robot can execute those instructions and move itself without outside help. The second element is the ability to perform complex tasks. This implies that the robot does more than a simple repetitive motion. It must have some ability to think and determine the best sequence of actions to perform in order to complete a task. We call this the ability to plan. What is not mentioned in the definition of the robot we decided on earlier is that the robot must be able to sense its surroundings. In order to successfully plan and act, the robot must first know what is around it in order to decide what to do and how to do it. For example, in order to move to a new location, the robot must start by sensing where it is now and continue to sense as it moves so that it knows when it's done. Put all together, the robot must be able to sense its surroundings and its own position, plan what needs to be done and in what order, and then act on these plans. This sense, plan, act framework is commonly used by roboticists to describe a robot and the order in which it operates. Now let's look at these elements in more detail. As an example, I want the robot to mow my lawn. Simply telling the robot doesn't tend to work very well. Hey robot, come mow the lawn. Instead, we need to provide instructions to the robot.
It's just like explaining something to a small child. You typically can't tell a robot to do something complex without first telling it how to do simple things. In the lawn mowing example, we simply have to break down our task. The robot needs to determine where it is now, figure out where to move next, then go there. And it needs to know when the lawn is completely mowed. And those simple instructions equate to what a computer programmer would write to accomplish the task. Find your position, find your next position, move there, all the while monitoring itself to make sure the work is done. You can see how the program corresponds with the instructions.
The first part of our framework is sensing. There are a few things the robot needs to sense in order to mow our lawn, such as, where am I in the world? For this, it needs two things, a position and a map. The map tells the robot where things are around it. It may also have additional information that tells the robot what kinds of things they are. Our map can tell the robot where a tree or building might be located, so it doesn't run into them. It may even help out by marking such things as sidewalks and roads. For our lawn mowing robot, it would be good to know where the grass is and where the garden is. It's even more useful if the robot knows where it is relative to these things. For example, knowing its position relative to the building lets the robot know if it needs to maneuver to avoid the building now, or if it can ignore it for the time being. The robot gets this information when it knows its location on the map. Once it knows that, the robot figures out which way to go to reach its goal or how to get around an obstacle. Another question that needs to be answered is, am I done yet? There are many ways to sense this. The robot can monitor grass height and keep going until it's all short enough. Or it could keep track of where it has been and make sure it covers the entire yard. As roboticists, we look for good ways of determining when the job is complete that are hard to get wrong, yet easy to check. Our lawn mowing robot now knows the location of the grass and its own location. It can also tell that it's not done mowing the lawn yet. But what does it do next? This is the part of the framework we refer to as the plan step. We can think of this as answering two questions, what to do and how to do it.
Our robot has its task and knows what's around it. Now it needs a destination or goal location, and it has to figure out how to get there. If it's a flat, wide-open lawn, this task is easy. The robot can point in the direction of the goal and drive straight at it. But what about a tree or bush in its way? Now it must figure out how to get around this obstacle on the way to its goal. In a yard, there may be many obstacles, all of which need to be avoided. Figuring out its path is a key part of the plan step, and we typically want it to choose the best path, and what's best depends on the situation. Maybe we want to get the lawn done quickly so we can move on to other things. Maybe we want our lawn mowing robot to choose the path that minimizes fuel consumption. And if we're mowing a baseball field, we might want a special pattern in the grass. In all of these cases, somebody has to tell the robot how to judge what is best.
The robot now knows the map and its own position on it. It knows it's not done yet, and also knows the path it will be following. The last part of our framework is the act step, the actual movement along the robot's path. To make the robot move, it must send commands to its motors or other actuators and tell them to move. Usually, we want robots to move a motor at a certain speed, so we monitor the robot's motion, telling it when to speed up or slow down. The part of the robot that runs the motors or actuators is called the controller, since it controls how the robot moves. Robots use all different types of motors, electric, hydraulic, air-powered, also known as pneumatic, and many others. These actuators can control wheels or legs or tracks or arms or other parts of the robot. allowing it to move with great accuracy, impressive strength, or lightning-quick speed. Now that we've looked at the Sense, Plan, Act framework, let's look back at my crashed UAV and figure out what went wrong with it. The robot had an error in sensing its environment. Since it thought it was too close to the ground, it planned to go up and get to the correct height. It then acted on this plan and applied power to the propellers, which directly led to the impact with the ceiling. Here is the UAV flying again once we got everything fixed. In this case, it is sensing correctly and planning and acting accordingly to fly around the room. In this session, we discussed the Sense, Plan, Act framework. Sensing is the process of gathering information about the robot's surroundings. The plan step is the process of making decisions on what and how to perform the next action. And finally, the robot performs an action, where it executes the plan and moves. You should now be familiar with the Sense, Plan, Act framework, and you should be able to name some examples of each step. Now, the challenge questions for this lesson: figuring out the Sense, Plan, Act steps for two different robots. Imagine you have a robot surveying an orchard, looking for ripe fruit to pick. What are the Sense, Plan, and Act steps for this robot? What should it sense? What plans does it need to make? What are its actions? Now imagine you have a robot vacuum cleaner. What are the Sense, Plan, Act steps for this robot? What would it need to sense? What kind of plans would it need to make? And what are its actions? Then look at which steps are the same between the two robots, which steps are different, and why. Finally, look at how the plan changes if the criteria for best is using the lowest amount of energy instead of the fastest time. Again, for a robot in an orchard examining fruit, what are the Sense, Plan, Act steps? Do the same for a home vacuuming robot. Then explain which steps are the same and which are different. And tell us how the plan changes using lowest energy instead of fastest time. I'm John the Robot Doctor. See you next time. Hey robot, go take out the trash.
You can find these video lessons online at wqed.org/therobotdoctor.